So far, we've talked about Newton's laws. At least the first law, an object in motion wants to stay in motion. That is, if it has a constant speed, it's going to continue in that direction with that speed until some force acts on it to slow it down or change its direction. And that force could be friction, so it doesn't look like there's a force, but it's still there. F equals ma. All of the forces added together tell us the acceleration. Now we're going to talk about Newton's third law. And the first thing to know about Newton's third law, you probably have heard it, a reaction has an equal and opposite reaction. And that's a fine way to sort of keep it in your head, but it doesn't actually help us a lot in a physics class because it can sort of hide what's going on. And it's a little tricky, the third law is. So I'm going to set up an example because I think it's easiest to sort of see when I have a setup like this. So I've got two blocks. There's still no friction. We're not ready to get there yet. So it's on like an ice rink or an air hockey table, something like that. And we're going to tie a rope and pull this bigger block to the right. So that's our force tension that's acting on the first block. So if I make the force diagram for my block 1, so this is block number 1 and block number 2, then it has a force like this. It has a weight going down, right? So I'm going to make that fairly big. M1 times G. Let's say this is M1. This is M2. And then we'll say that because there's a table or a surface supporting it and it's not accelerating up or down, then we must have that the normal force on 1 is equal to this because these two together give us no acceleration. So far this looks like it's accelerating this direction on the page. Okay, object 2, we look at block 2, and it's got a smaller mass. So I'm going to put, because it's smaller, we'll assume it's a smaller mass, M2, G down, also a normal force, normal 2. And if we just leave it like this, we look and we say, hey, there's no acceleration here. These just balance each other out. But of course, there is some interaction happening right in the middle here, right? It's not like this tension force acts only on block 1. Somehow, this pull is actually pulling both of these blocks, and it's doing it because when 1 gets pulled to the right, it of course pushes into 2, which pushes it to the right. So there is this force. It's really a normal force. It's the surface of this block hitting into block 2. This is the force of block 1 acting on block 2. And similarly, block 1 feels a push back on 2. 2 is like, hey, I don't want to go anywhere. I'm happy at rest, for example, when we start. So block 2 then pushes back on 1, and this is where the third law comes into play. Force of block 2 on block 1. Okay, and so these are our third law pairs. And notice right away that these third law pairs, as I call them, act on two different objects. So they don't ever show up in the same force diagram. We've got the force that's on 1 due to 2, and the force that's on 2 due to 1. So you can, some people write the subscripts this way, and some people write them like this. It doesn't matter to me which way you do those, as long as you label them. And if you want to just call them an interaction pair, that's okay as well. But these are on two different objects. They never show up in the same force diagram. So let's look at another example, and then we'll try to get a little more sort of general expression here. So I've got two, let's say these are the same mass now, and it's just hanging here, so there's no acceleration. So we've got, this has an mg, and this also has an mg. And then because there's no acceleration, there must be this force of tension up on the bottom mass. But then what happens here is this feels the pull, this force of tension down this way, right? In the other direction, this pull from the bottom one. And so its tension force up here, I guess I'll do it with this, with green, must be like this. This force tension in this rope needs to be equal to this plus this. These two added together have to equal that one. Okay, and again, our third law pairs in this case are really these pink pairs that are acting as tension pairs, right? Those are our third law pairs. Okay, so they have to, if I'm circling them as third law pairs, they have to act on two different objects. Okay. You say, wait a minute, I see some other forces that are equal to each other and they're in opposite directions. Aren't they third law pairs? Well, let's take a look at those. So let's take a look at an object just sitting on a table. Okay, so I have a box on a table and we can certainly see we've got mg that's down and we have a normal force that's up and it's just hanging out. Those are not third law pairs. They're acting on the same object and they have to act on different objects. So what's the third law pair? Well, if I draw my table, the equal opposite force of the normal force, we can write this is the force, or we can say this is the force of the table on the block. So then the pair is a normal force of the block on table. So notice this one shows up in the table's force diagram. The other forces over here, but those are the third law pairs. And so similarly, this blue is the force on block due to Earth. Gravitational pull. So that means if we look at the Earth's force diagram, there is in fact a gravitational pull acting on the Earth due to the block. It pulls up on the Earth the same way the Earth pulls down gravitationally on this block. And that and these are the third law pairs. So these blue ones go together and these orange ones go together. But a lot of times we don't care about what's going on, what the Earth's force diagram looks like or the table's force diagram looks like. We often just care about the object that we're interested in, whether it's us, whether it's a little speck of, I don't know, sand somewhere, whether it's a ball that's in the air, anything that's moving and we want to describe its motion, we need to then figure out what the forces are on it. And we don't worry so much about its impact on the world. It's kind of a self-centered way of looking at things. When you build a force diagram, you want to think in terms of being very self-centered. What is the object experiencing? If I want to know my force diagram, what am I experiencing? It doesn't matter what I'm doing to the rest of the world. And so when you look at a force diagram, you want the forces on the particular object due to everything else outside it. And then if you need to see, if you've got two objects like this that are interacting or like this, then you're going to have to pay attention to these other, to the third law pair, force pairs.